Okay, so I was gonna do a slideshow. It's kind of like I can't quite figure it out. So it's my pleasure to present my work here, and thanks Dimitri and Brian and Edward for the invitation. I hope I won't be wasting the audience's time, hopefully. So we're gonna be talking about the rigidity of Neumann spectral gap in spaces that possess negative curvature, in the sense that we want to work with spaces with non-negative Ricci curvature. So in particular, it covers the spaces with the sectional curvature bound by 0 or negatively curved Alexandrov spaces or Bakry Emery spaces with Bakry Emery tensor larger than 0. Kind of falls in the same category. So I'm going to start. I didn't know if I should present lots of details or be more or do more of a skimming of my work. So I start with some easy stuff and then try to somehow draw some pictures. So everybody knows about the Laplace operator, and the reason we use Laplace operator is that anytime you want to see you want to model diffusion, or you have to use Laplace operator because, for example, if you consider the Brownian motion from the analytical point of view, then the probability of seeing some particle in a region is evolving in time by the heat equation. So this would be called Fokker-Planck equation for that process. From the geometric point of view, or maybe again analytical point of view, when you want to minimize energy, like a stress tensor energy, which is given by the Dirichlet energy functional, then if you take the gradient flow of this energy, it would be the heat equation, and the Laplace operator again shows up. Well, there are other versions, like if you add some non-uniformity to the space, then you have to account for non-linearities in your heat equation. But nevertheless, again, you have some elliptic operator resembling the Laplace operator, some multiple of the Laplace operator. And you work in the geometric analysis, or Brian work in the mean curvature flow stuff, and people who work, I see people that are experts in the geometric flows. They know that these kind of parabolic equations or weakly parabolic equations, they appear all over the place when you work in geometric analysis, especially with geometric flows. And for those who work in areas like stochastic processes, then again they sort of have the same concepts, but with different using different lingo, basically. Or even people who work in physics, quantum physics, when you consider the Schrodinger operator, then you are sort of solving a complex wave equation, which is again written using the Laplace equation. So I'm just rambling about the use of this diffusion and the Laplace equation. But by the way, the wave is not a diffusion equation, but I mean, nevertheless, it uses the Laplace operator. Or if you want to embed a manifold or a space into L2 space, then you can again use the eigenvalues of Laplacian and get a good embedding, which is almost isometric, depending on where you cut depending on how many you use. So everybody knows the concepts of eigenvalues. So if you have an operator, then the eigenvalues are defined in this way. So if you have the Laplace operator, we call lambda to be the eigenvalue. If Laplace of u is negative lambda u, the negative here is because, well, geometers use perhaps lambda u, or the other way around, or another people from analysis use minus lambda u, but it's because we want to work with positive numbers. So we put that minus sign there. And as you know, we can, but depending on what kind of boundary conditions we impose on on the space, then we get a different spectrum. So, so we can get Dirichlet eigenvalues if you put Dirichlet boundary conditions, which is equivalent to minimize the Rayleigh quotient in the Sobolev space of basically compact support functions, H0, 1, 2. Or if you just, if you minimize the same quotient in W1, 2 without this zero subscript, it means that we are computing the Neumann eigenvalues. So depending on what kind of boundary conditions we want to impose, we work with different Sobolev spaces, and that gives us a different spectrum. So these are standard stuff that there's like a simple positive eigenvalue, and then it diverges to infinity. And the Neumann eigenvalues, they start from 0, and then not necessarily simple, and then diverge to infinity. We can also tweak with the boundary conditions. We can impose a mixture of Dirichlet and Neumann boundary conditions, or like some or a linear combination of those conditions. And this way we can get different kind of problems, different boundary value problems that we can solve. So these are very standard stuff. Maybe Steklov eigenvalues are less kind of less known, not less known, but maybe like less usual to see in or to work with. And so for these eigenvalues, actually they have lots of applications in free boundary minimal surfaces, where the works of Shane and Fraser, where they studied free boundary minimal surfaces within a ball. And so the way we define them is that basically you take an on the boundary eigenvalue of the usual derivative operator, du dn, and then you look for a harmonic map that has that boundary condition. So these are, yeah, so these are basic ways that we can define eigenvalues. But arguably, the Neumann eigenvalues are the most natural ones, since, well, if you write the divergence theorem, there is a boundary term. And if you wish to just minimize the Rayleigh quotient without basically caring about the boundary, then the most natural condition to have is the boundary conditions, so that the boundary term would vanish. And this is the viewpoints in spaces that don't necessarily have a well-defined boundary, or maybe they have a well-defined, but this is a very usual way to define eigenvalues for spaces that the divergence theorem doesn't necessarily hold in the sense that there is a boundary term. So that's why in the spaces that I'm the RCD spaces, which basically are metric measure spaces, we have to use minimize the Rayleigh quotient and call it the eigenvalue, which means basically we are computing the Neumann eigenvalues. Some other standard things about eigenvalues is that the regularity of eigenvalues, we can in the interior you have the analyticity of eigenfunctions, and then boundary regularity, of course, depends on the regularity of the boundary of the domain that we are considering. So I'm gonna just pass and then just say that, and then move to the next point. That's a very delicate issue, the boundary regularity of an eigenfunction, or even harmonic functions. That's not an easy thing to do in this talk. As for the computation of there is the Maximin principle of Courant, which basically is well, for the first one you just minimize the Rayleigh quotient, but for the next ones, as you know from linear algebra, you have to exclude the cases that you already the directions that you have already discovered in your eigen directions, and then minimize over the complements of that space and then maximize. And this way you obtain the higher eigenvalues. depending on whatever the Sobolev space you are using, then you get the corresponding eigenvalue, either it being the Neumann eigenvalue or the Dirichlet eigenvalue. And some standard Fourier analysis or eigenvalue analysis basically tells you the things that you expect to hold, like the Parseval's formula. You can always expand your L2 function in terms of the eigenvalues, and the norm is basically norm squared is the sum of the squares of the norm of those normal modes that appear. And of course, you can solve the heat equation starting from any initial condition if you know the eigenvalues. Okay. Now let's get to the more towards the subject of the talk. So what is the first gap? The first spectral gap usually refers to the, well, depending on if you're working with Dirichlet or Neumann eigenvalues, depend on the first non-zero one. Or sometimes in physics, it's called the principal eigenvalue. And the goal in this talk is to say that if in non-negatively curved spaces, if this sharp bound that I'm going to say, we're going to discuss that it holds, if this sharp bound is achieved, then the space has to be one-dimensional, which means there's very strong rigidity in the sharp spectral gap. What are the uses or implications of having a spectral gap or estimate for spectrum? Well, it's from analytic point of view, it tells you how fast processes that are Brownian-like are converging to their equilibrium. Or from the geometric point of view, we can talk about the isoperimetric inequality and the relation between eigenvalues and the isoperimetry problem. And for example, there is the theorem which says basically having the eigenvalue, well, you can pick out the ball from other subspaces with the same volume based on the fact that it was first eigenvalue. Also, you can do this in Riemannian manifolds with some, well, you need some preparation for that. For example, if you want to do the on Riemannian manifolds, then you have to compare you have to pick a model space, which would be your space forms, and then you can see the proof of this in the book about isoperimetric inequalities. Anyways, this is doable on manifolds too. So there is a very intimate tie between isoperimetric problem and the eigenvalue problem. Also, one can talk about the second spectral gap, which is much harder. Well, in some, it is harder. It's much harder than the first spectral gap. And there is, well, I might not be too updated on this second spectral gap, but as far as I've seen, the Wei, Gufang Wei, and her collab results were the latest things I saw on this. And then also there is a fundamental gap conjecture, which was settled by Andrews and Clutterbuck, which basically says if you have a convex domain in Rn, second spectral gap is bounded below by that ratio that you see, 3 pi squared over diameter squared. What we are going to see is that the first spectral gap is bounded below by pi squared over d squared in curved compact spaces. Okay, so let's see some folklore stuff or maybe some metaphors. So basically, when you talk about the result, it's like you want to see how much of the geometry is determined by the eigenvalues, and in this case by the first eigenvalue. And of course, everybody knows about the COSC question, which says can you hear the shape of a drum? The answer is no, and you can come up with isometric spaces, isospectral spaces, which are not isometric. And there are many results in this direction. I just here, you can look it up and see what kind of examples are there. So I made a metaphor myself about this one, which is a bat cannot become a successful drum player. And that's because, well, a bat can only hear things. So it can only hear the spectrum. And because you can't hear the shape of a drum, the bat cannot be a successful drum player. But at the end of this talk, we will see that it can actually play instruments, which would be a one-dimensional, like a like a circle player or something. So let's do some. Well, this thing that you see here in the middle of this is basically a poem by Attar of Nishapur, which basically it refers in a very elegant way. It says that seeing is not the same as hearing. So I just thought it would be nice and related to the subject to put this poem here. Okay, so back to the math. So the question arises: what can we, what kind of geometry or what quantities from geometry we can figure out? Can we figure out from the spectrum? And well, some easy answers are the heat trace. We can, if you know the spectrum, we know the heat trace. And the heat trace also encodes some curvature functions as its coefficients. For example, A0 is the volume, so we can know the volume of the space. We can know the scalar, the total scalar curvature of the space, and we can know some curvature functions like this one, scalar squared minus norm Ricci squared minus 10 norm Riemann squared, the total of this quantity. Okay, but we cannot know the metric, basically. That's what I'm trying to say. So let's talk about how one would derive eigenvalue estimates if one has Ricci curvature. Perhaps everybody can guess that you have to use Bakner identity, because in the Bakner identity you have both Laplacian terms, you have some terms with definite signs, we have Ricci curvature, so this would be the most natural place to start from. And if you have Ricci bounded below by some number k, in this sense Ricci larger than kg, then you can just in the Bakner form. This Bakner formula is written for the Bakry Emery tensor, but it basically the same formula holds for if you put if you take phi to be a constant function, then this would be the usual Bakner formula for Laplacian. So if you use an eigenvalue, then I can put minus lambda u for delta u here, and then for Ricci I can bound it below by kg, and this term, the Hessian term, is non-negative, and if I use maximum principle at some maximum or minimum of this delta u, I can figure out, well, you can bound in the maximum of delta u, this should be non-positive. In the negative, it should be, in the minimum, it should be non-negative, and then that way you can get some lower bound for the lambda one. Well, you have to do this more carefully, as I said, but the main idea is that you use the Bakner formula and maximum principle. So depending on how much work and effort you're willing to put in, you get perhaps less sharp or sharper results. And for example, the famous Lichnerowitz bound, if k is positive, then lambda 1 is larger than n over n minus 1k, and which is sharp actually, and the rigidity is due to Obata. So this holds for spheres. And for non-negative curvature, the story becomes a little bit harder, because you don't have much convexity in the space, in a sense, because the k changed from positive curvature to non-negative curvature. So many Maxwell type arguments that you would use you have to use them in a different way, perhaps, to get results on the to get bounds on the eigenvalue. So the Li's famous bound is for empty boundary and non-negative Ricci curvature. Lambda 1 is larger than pi or squared over 4 times d squared, which is not sharp. Obviously, for the circle, it's not sharp. It's pi squared over d squared. And Li alone, he has, I guess, well, it should be in his geometric analysis notes, I guess, or maybe some, I forgot where it is actually from. If K is non-negative and boundary empty, you can boost this bound up to pi squared over 2 times d squared. And Yang, Zhong, finally, they gave the sharp bound squared over d squared, which holds for the circle. Well, this didn't come out of nowhere, because like previously in the 60s, actually, Payne-Weinberger, Payne-Weinberger, they proved for convex domains in Rn that basically this bound holds for convex domains in Rn. So this is a generalization of that result. Much different. The proof is Payne-Weinberger's proof depends on symmetrization, and this proof of Yang and Zhong is basically a modification of Li and Yau's arguments, which again relies on the doing maximum principle. And yeah, so that was for empty boundary. For convex boundary, you can basically get the same results, and that's due to Yang in 99. You can do other types of estimates. Basically, you can derive a mixture of like a combination of positive bounds and then non-negative bounds, and there are many works in that direction, so I don't want to say it's just like one paper. For example, like there is the work of I guess and Rollets and many other people that they have these kind of bounds that you can basically get a mixture of these like Rishnerowitz types bounds and Yang-Zhong type bounds. But nevertheless, the sharp one is pi squared over d squared. Okay, now we move to the basically the how, or basically if depending on the curvature, how would you bound the eigenvalues using comparison principles? This again is from the collected work of many people. So, but perhaps Bakry Chen is the important. Bakry, Kroger was the first one, I guess, that came up with the like one of these comparison principles. But then Bakry Chen, and then Chen and Wang, and even Andrews and Clutter for the case of Bakry Emery tensor, they derived these kind of comparison principles, which says if I know the bound on diameter, dimension, and the Ricci curvature, then I can compare my my principal eigenvalue to the eigenvalues of some Sturm-Liouville problem, one-dimensional Sturm-Liouville problem. Well, Sturm-Liouville problems are one-dimensional, and that would basically this is a very nice comparison result, because you are no matter what the dimension is, well, it matters, but never once you figure out this constant lambda hat, then you have a very nice lower bound for the first eigenvalue. Okay, so the drift term in this Sturm-Liouville type equation is given by this function. You might have seen this kind of functions a lot in this in the topic of curvature bounds, and it also appears here in the comparison principle. So how would one go about proving such comparison principle? Well, it's a very hard task to show this kind of comparison principle, but the gist of, well, the first step would be to say, if you take an eigenfunction of this Sturm-Liouville type problem and you compose it with you compose your eigenfunction u with the inverse of this eigenfunction, then the grad of that function would be less than 1. Well, you need some other conditions for that to hold, but nevertheless, like the main step in improving such comparison principle would to prove that gradient estimate. And that gradient estimate is proven via using the maximum principle. So now this kind of comparison principle for the eigenvalues have been generalized to less regular spaces. So to Alexandrov spaces, to Finsler manifolds, which Finsler manifolds some people might not consider it as less regular, but it kind of is, because your norm is not quite convex at the zero section of your tangent bundle. So, well, we can put it in category as well. But it's very different from the other things that appear here. It's not easy. It has a very nonlinear kind of nature to it that differentiates it from the other things that you see here in this slide. But basically the same comparison principle holds in these less regular spaces or settings. So for Bakry Emery tensor, again, same comparison principle holds. And that's due to Bakry Chen in their paper. They talk about the CD conditions and using the Bakry Emery formalism, using the gamma 1, gamma 2 operators and the person, which is a generalization of the Buckner inequality to this, using it's like saying Buckner inequality using different kind of objects, different operators. Andrews and Clutterbuck, Andrews, Ni, and Millman, Vitali Millman's son, actually. And these different works in this direction that show basically the same comparison principle for the Bakry Emery. For Alexandrov spaces, this is due to Chen, Zhang, Zhu, and Wang Sha for Finsler manifolds with weighted Ricci curvature, which is defined similar to Bakry Emery Ricci curvature, but you have to use the Ricci from Finsler for Finsler manifolds. And Christian Ketterer, Zhong Yang, and Cavaletti Mandino, they have comparison principles for all these spaces. Ketterer only for positively curved RCD spaces, Zhong Yang for positively curved curvature spaces, Cavaletti Mandino, they did the whole spectrum. Basically, they showed the same comparison holds for all K. But they actually discussed the rigidity too, but they couldn't, only for the positive case, because the positive case required different, more standard tools than the non-negative case that we're gonna see shortly. Okay, so we talked about, so the setting of non-Riemannian spaces, as you can talk about Finsler spaces, Alexandrov, CD, RCDKN, or even discrete spaces, which I haven't seen anything in the getting rigidity and comparison and these kind of things is very hard in the way. I can't say hard, but because the Laplacian doesn't really behave in any particular way. It's not a diffusion operator, and it's just it's more or less a kind of a mess in the discrete case. So, but the other ones kind of they follow the same principles and the same laws. So let's talk about the singular framework for a bit. So everybody knows about metric spaces, metric measure spaces, and yeah, if you want to talk about weak notions of curvature, you need model spaces, which is your space forms, and then you can talk about spaces with basically with the weak sectional curvature bounded below or bounded would be Alexandrov spaces or cat spaces, Cartan Alexandrov Toponagov spaces, and or some people call all of these Alexandrov bounds. Well, everybody knows that. I'm pretty sure everybody here knows the definitions of these bounds using the Toponagov comparison principle for geodesic triangles or hinges, or using the, well, which one has larger size or which one has larger angles, and the more the curvature is, the thicker the geodesic triangles are. But weak Ricci curvature, they are harder to define, and everybody knows again the history of this, and this goes back to basically the work of Storm and independently Lotan Villani, which developed weak Ricci curvature bounds for metric measure spaces using convexity properties of, well, you have to use convexity properties not of a like a distance function that you would use for Alexandrov spaces, but you have to use the convexity properties of some, like an averaged quantity, because this time Ricci is the average of sectional, so perhaps any type of weak definition that you want to propose has to work with measures and averages, and this time the definition is basically the convexity of the entropy along some geodesics in the probability, which would be the optimal transport geodesics. I took this picture right out of the first Google search that I did, so because I tried to draw this, but this was nicer, so I gave credit here to the person who drew this. And if you see this picture, so you know where it came from. And so the idea of this Storm-Villani definition for Ricci curvature bound is that we want, well, consider the sphere. If you want to say the sphere is positively curved, then when you do optimal transport, which is basically you want to move a mass one measure from one spot to the other spot, minimizing the costs. And if you take the cost to be basically the d squared, and now the question arises, why would you take d squared instead of like some other power of d? And that goes back to the fact that anytime you use the L2 sort of norms, you get better linearity properties. Nevertheless, if you use the d squared as your cost function, then you can define the optimal transportation doesn't need the cost to be d squared, but this whole theory relies on taking it to be d squared. Then you know that the optimal transport, when you move some mass one measure from one spot to the other spot, the integral of d squared to be minimized over the coupling measures that you take, which tells you the coupling measures that tell you how much of the mass from one point here, x, is moved to the other point on the support of the other infinitesimal, basically, description of this mass transfer. There are various ways you can define this optimal transport problem. You can talk about the Monge problem, which starts with a map that actually tells you where to put this portion of the mass, like each point where it goes. But you can start with the weaker version and the counter-Ricci version. And nevertheless, on many nice spaces, you still get a unique transport map T. Anyways, so the lower Ricci curvature bound is defined by the convexity of the entropy. And the idea is that if you take the sphere, on the sphere, if you optimal transport some mass around the north pole to the south pole, then basically you have the sense that you have to move the mass along the geodesics, which are portions of gray circles. And as you do this transfer, then when you get closer to the equator of the sphere, the mass that you started from, it has now larger volume. So that means it is less Ruli, basically. So it has larger entropy. well, because it's convex, so it has to have less entropy. It's a larger volume. And then once you get to the south pole, again, the same mass is concentrated in a smaller volume, so you get larger entropy. Entropy in this sense, some people put a negative here. This is basically, some people call this the Kullback-Leibler entropy. Some put a negative sign here, then that would be concavity of that entropy. Depending on what sign you put here, this convexity concavity statement would change from one to the other. But if I take the entropy to be log, the integral rho log rho, rho is the density of the probability measure that I have at time t as I'm doing this optimal transport, then this convexity, it basically has, it doesn't say anything about the dimension of the space, but it says that the Ricci curvature, if I was on a Riemannian manifolds, this would be equivalent to Ricci curvature being larger than k. And for that reason, we call this to be CDK infinity, which means it doesn't really limit it doesn't say anything about the upper bound on the dimension, but it says that the lower bound cannot be less than k. If you want to be more precise and get an upper bound for the dimension, then this convexity has to change. And for the entropy, we have to use Renyi entropy. And this convexity takes a much more complex, but it's manageable. And the idea, basically, the idea is the same, essentially, but you have to use some distortion factors here in your, you have to incorporate some distortion factors in your entropy, definition of entropy, and this convection, and that makes the statement harder, but the ideas are the same. So convexity of this entropy is equivalent to Ricci larger than k. If you wanted to also capture the dimension, we have the dimensional version of this convexity. So these CDK infinity spaces or CDKN spaces are not really still, I mean, they're not nice enough for us to do some geometric analysis generalizations. You can do some, you can generalize some results from Riemannian geometry to CD spaces, but still cannot be necessarily generalized to a CD space. And that's because these spaces also basically contain Finsler spaces. So whatever doesn't hold for Finsler spaces, you cannot prove for CDK infinity spaces. So basically you have to impose a condition that exactly for that reason to just exclude Finsler spaces. And that would be, I want my space to be infinitesimally linear in the sense that I want the Jigger energy to be a quadratic form, or said differently, I want to be able to take the inner product of the gradients of functions at any point. Or said another way is that I sort of define some sort of Riemannian metric on this space. Well, not nobody says you can define a Riemannian metric on this space, but the idea is basically the same. So you want the Jigger energy to be, is basically how you define Dirichlet energy in this weaker sense. So if I want to define the Jigger energy for a function, then you have to approximate it by Lipschitz functions and then take the Dirichlet energies for that sequence. And the functions that admit such finite Jigger energy, we call them to be basically in our Sobolev space, the 1-2 space. That's how you define the 1-2 space. Dirichlet energies should be bounded. And so this energy being quadratic is the definition of infinitesimal Hilbertianity. Okay. There are many other ways, basically. There are maybe 4 or 5 other ways to define the same Sobolev space on metric measure spaces, which I'm not going to get into. Like some school is the Shan-Mugyalingam, and then the Koskela, and then some other, You cannot say all their names, but that's one school. And then the Ambrosio, Gili, Savare, they are one school. And some Japanese schools like Shiyoya, Kuwai, and some other mathematicians. There are many ways to define Sobolev spaces, but basically in this particular setting, 3 or 4 versions that exist, they all coincide. So for us, the W12 space is the spaces that have Cheeger and the functions that have Cheeger energy, finite Cheeger energy. Okay, so if in space which is infinitesimal Herbartian, then we call that to be an RCD, R for Riemannian, because we basically assumed some infinitesimal Euclidean infinitesimal inner product gradients of functions. Okay, so we discussed the rigidity results. If in Obata proved the rigidity for the Lishnerowitz bound, which if the bound is achieved, then the space has to be a sphere, the n-dimensional sphere. Payne-Weinberger, they proved in the non-negative case in the plane for convex domains, which can easily be generalized to the convex domains in Rn. The same method works. And Hang and Wang, they showed if you have a compact manifold without boundary. And actually, what I wrote here is not correct because they don't discuss the convex boundary. They only discuss if you have a closed manifold which achieves this sharp bound, then it has to be a circle. But it also is true that if it has convex boundary and achieves this bound, then it has to be an interval, if it's connected. So in the RCD setting, the rigidities are, as I said, the Christian Ketterer's result for K positive and N finites, and the Cavaletti-Mandino for the positive K, Gili, Ketterer, Kawada, Ota for, again, positive K and no dimension bound. And Finsler is due to Wang-Sha. So let's get to what we want to, well, I'm not going to prove it here. So I'm just going to list some stuff. What we showed with Christian and Kitabeppu, is that if we have an RCD, non-negatively curved RCD, and with synthetic dimension bound, so it has to be RCD 0n, and full support as is usual that we assume for this kind of problems. And if the same bound is achieved, X is either a circle or line segment, and M is also constant multiple of H1, the Hausdorff measure. I should say that why do we know that this spectral comparison holds for RCD spaces, and that's due to Cavaletti-Mandino's work. So we know that the same bound is true for these spaces pi 2 over d squared. If the bound is achieved, we want to show that it's one-dimensional. Now this question, well, as I said, this non-negative case is much different from the positive case. In the positive case, you can use basically different techniques. If you use the Hessian or the self-improvements and the Hessian formulas in RCD spaces, then the positive K that appears gives you, well, it actually, in some step, you can that cancel out that positive K from both sides and then get what you want. But in this case, if the K is 0, that the same proof doesn't work. Let's just say that. And I will talk about how actually one would prove this rigidity result. But let's talk about some of the corollaries of this. So, once you prove this rigidity bound, then you can talk about almost rigidity. So I'm not going to explain all of these corollaries, but we can talk about almost rigidity, for example, which is if you have a sequence of manifolds and they don't have non-curvature, but their lower bound on curvature is minus delta, and delta is decaying to 0 or approaching 0. And lambda 1 is also very near pi squared. And diameter is, well, we normalize diameter. Diameter is less than 1. If you take diameter to be d, then you have to take this to be like pi squared or d squared plus the delta. Then you can, for every epsilon and this apparatus, you can, so let me just say it more precisely. For every epsilon and n, you can find the delta such that if your initial apparatus is within delta of the rigidity problem, then your spaces are within epsilon distance to the one-dimensional space. So the other ones I'm not gonna talk about because the time is also running out. One other, well, maybe like the last one, which is if you want to get a bound on eigenvalues of bubbles in any Riemannian manifold, then you can, as long as you allow the radius to be small enough, you can, again, using the same ideas as that almost rigidity result, you can again get similar bounds for the eigenvalues if you allow this theta to be small. And you need the non-collapsedness in your space. Anyways, so I'm just going to talk about some stuff that you need to do for this rigidity result to prove this rigidity result. First, you can rescale everything and make your problem nicer, but by taking diameter to be pi, lambda is 1 because you say that the bound is achieved, so lambda is 1, diameter is pi. And then you have to use some technology, new technology in the RCD setting, which is you have to reduce the problem to the one-dimensional case. So this goes by needle decomposition basically in the Riemannian manifold case. It's called needle decomposition. In this case also, anytime that you have, I'm going to show you the statement later on, but anytime you have some nice globally Lipschitz one function, you can talk about basically the flow of gradient of f. That's the whole idea. So basically, if you have a globally one Lipschitz, I mean, look at every point, if the Lipschitz constant is 1 for function f, then you can talk about you can't talk about its gradient of f, but you can talk about the flow of its gradient of f. And that's the whole idea of 1D localization. And Cavaletti's work actually tells you that when you do the 1D localization, the lower bound on the curvature stays the same. So that basically reduces your problem. It's a very strikingly useful technology in RCD setting because basically you can reduce many things to 1D case, and it's just amazing. And it started in Cavaletti's work, and in Cavaletti-Mandino's papers, there are 2 papers about this 1D localization. They actually kind of perfected the whole thing. But the 1D localization actually goes back to Millman and many other people who worked in this direction. Also, yeah, in the Riemannian case, I guess, well, in this case, it's due to Cavaletti-Mandino, and also, yeah, Cavaletti would be the first one for the RCD spaces to talk about the 1D localization. And the other things that we need for is that in the Riemannian proof, you want to say that this when you take the eigenfunction for this extreme case, the u squared for plus gamma plus lambda u squared is constant. It's constant 1 on the whole space. In the Riemannian case, this is done using the maximum principle. And first you apply Buckner and then you apply maximum principle. But in this case, when you start with an eigenfunction, you don't know, you know that you minimize your Rayleigh quotient in the Sobolev space. So delta u squared is just, its energy is bounded. That's all you know. You don't even know that this delta u is even continuous or anything of that sort. So the first thing that you would do is that you should prove some regularity for the norm of gradient u squared, or norm of gradient u. And that is where you have to use 1D localization. There is, I'm not seeing any other ways that, I don't think you can, maybe you can do some, there is some other, the Georgi-Nash-Moser theory for this space, for the weak or metric spaces, might be able to use, but even for using that, when you want to say that the Georgi's condition hold, you have to use 1D localization, perhaps. There's just no way around it, perhaps. I mean, as far as so far, I guess there is no way around. So you have to show some regularity for delta u squared. That's the hardest part, because I mean, how would, if you didn't have the 1D localization, we can do this, that this is Lipschitz or is in the Sobolev of space to work with, to be able to work with it. So that's one difficulty, which is come by 1D localization, which I'm not going to go into the details much because it takes a lot. I mean, my time is also over, so I'm going to just move faster. Then the other steps are more or less similar to what you would do in the smooth setting, but each step doesn't just follow with the same computations. You have to basically do all the dirty work that you have to do in these less regular spaces to get the same. So the strong maximum principle that here you would use is basically the one that started with in the Bjorn work, and then maybe perfected by Gilly, and later on other versions that appeared by Gilly and Rigoni. So the other steps are basically sort of similar, and so I'm going to just in the smooth to reduce the space to an isometric product, and then you can use a diameter arguments to say that the space has to be that lower dimensional fiber. It can't just be a not zero dimensional fiber times a lower dimensional fiber, and that's the idea of rigidity. So the tools, but the tools here that you use are very delicate, because you have to use you have no regularity to work with. The space is just a metric measure space with some, well, it has some good properties, but it's not at all obvious how to do these kind of analysis. So some very, very useful techniques in this setting is the first variation formula, which tells you if you have an optimal transport plan, how you would take the derivative of a function in the direction of the gradient of that plan. That's basically the gist of this theorem, which is the first variation formula. So I'll explain all the details that go into the formula. The second variation formula, it tells you basically the relation between the Hessian and the second derivative of f in the direction of these optimal transport, or Wasserstein geodesic or optimal transport family of measures. And again, this Hessian term is, I mean, you can define it in the RCD setting by requiring that it, well, from the causal formula, you can get a closed formula without, we can get a non-local formula for the Hessian. You can define the Hessian in the same way, but then to say that it actually is any object that you can work with is again a very delicate matter, which is goes to the work of Gilly that's developed this differential geometry objects in the RCD setting. So, and then the strong maximum principle. This is basically the Bjorn's maximum principle. You can jazz it up a little bit to say that basically here you are seeing the same statement that you would see for the maximum principle in the Riemannian setting. So, well, there's work to go into proving this maximum principle, but the main parts are the maximum principle of Bjorn. So if you have a sub-minimizer of the Dirichlet energy, and then if it achieves its maximum, it has to be constant, as you would expect for in the Riemannian setting. So here, if you want to use this strong maximum principle, you have to also show that your the function that you work with is continuous. So if you show its Lipschitz, then that would give you the continuity. But to show its Lipschitz, not only in the Sobolev space, but is the same sort of regularity that I was talking about. The 1D localization, which is this statement here, I'm just gonna explain it in a very haphazard way. So if there is a which has its integral is 0, then you can make a Lipschitz 1 function that has Lipschitz 1 at every point out of this, and then you can do a 1D localization and find the gradient of the flow of the gradient of that function, and along that flow you can show that the fibers are these, like every curve that appears here, it would be a minimizing geodesic, and along those curves you have the density of your measure. You can do a disintegration of the measure and you get a one-dimensional, and it satisfies the same convexity as it would in a space with lower curvature bound by K, meaning that your CDK condition, lower bound on curvature, reduce the lower bound dimensional fiber on these one-dimensional fibers, almost all of these fibers. And then, so basically you reduce the analysis to 1D case. If you could basically start with if you have you have the right ingredients, the CU here, and all the hypotheses are satisfied, then you can use this 1D localization, which in our case, for the Neumann problem, you can formulate Neumann as minimizing the Rayleigh quotients with functions that are basically the integral of them is 0. So there are two versions that you can, two Rayleigh quotients that you can use to get the Neumann eigenfunctions. I should have put these formulas here, but for one, you can assume that the norm of the L2 norm of U is 1, and you minimize the rate, but then you get rid of the norm of U squared. You assume that to be 1, so you are minimizing the inverse of the Richter energy. The other version is that you assume U is not a 0, and then but its integral is 0, and then you minimize the Rayleigh quotient. These two would be equal to imposing Neumann boundary conditions. Okay, so, and what we were talked about, well, it's not, because it can hear, hopefully it's not deaf, it can hear, so it can hear the first eigenvalue, because if you couldn't hear the strongest one, it would be deaf, and so it can figure out they can figure out the shape of one-dimensional shapes like the stick and the circle, so it can play. Well, it's not, it's not, well, it's a bat, so what would you expect? So yeah, that's my talk, and thank you for your attention. Sorry, time for like 8 minutes. And